Okay. In this lesson, we're going to prove this theorem that if f is differentiable at A, then f is continuous at A. So we're going to start with the given. What is a given? F is differentiable. So the definition applies. And where do we want to end up? We want to end up to show that the function is continuous at A, right? Which is the three elements. The function is defined at A, limit exists, and the two are the same. Okay, so that's where we're heading. So from f is differentiable at A, so we're going to, just apply the definition. There are two of those. We're going to apply the second one. Okay, we're going to apply the second one. Now, when we are trying to apply the second one, by saying f is differentiable at A, that means this is true, and this one has a limit, And then we're going to do some algebraic manipulation. This algebraic manipulation goes like this. F of x minus f of A is equals to, of course, f of x minus f of A is the same as f of x minus f of A. But we're going to divide something. So we use principle number 1, okay, multiplying by 1. We assume x is not equal to A. Okay, so we basically rewrite f of x minus f of A in a different form by multiplying x minus A and divided by x minus A. Because when x is approaching A, x is not equal to A. So we can do this. So principle number 1 is applied. And then we're going to take limit on both sides. Okay, so we're taking limit on both sides. So we take limit on the left-hand side. Okay, and we're going to take the limit on the right-hand side. And the right-hand side, of course, we have two pieces. Each individual limit exists because this piece has a limit when x is approaching A by definition of differentiability, and x minus A also has a limit when x is approaching A, which is 0. So we can apply the limit law, right? We can apply the limit law. Limit law goes, we know limit law, right? These two items, this item has a limit and this item has a limit, so we can take limit respectively, separately. So we can take the limit so the limit of the product is a product of limits. So this limit and the other limit pieces. And of course, we know that the former limit is a derivative, right? Is this piece. The derivative of f at A. And this piece, the limit is 0, right? It's polynomial. So it equals to 0. All right. So now the interesting part comes. Can we separate these two limits? We cannot yet, because we know that f of A certainly is okay, right? But we don't know if f of x has a limit when x is approaching A. So we cannot separate these limits. So what we can only do is that we know that the difference limit is 0. The difference of the limit is 0. We cannot separate these two limits. So we're going to apply another trivial. Well, actually, even though it looks trivial, but you wonder how they think of it, right? Well, in order to create that, because we know that the difference has a limit, so what we do is that we're going to use the principle number 2, add 0. Okay, add 0. How do we add 0? We have f of x is equal to, right, f of x minus f of a plus f of a. We basically add a zero. We added zero. So now what do we have? We have this piece. We have that piece, right? We just proved it. And then, of course, we know where we're heading, right? We're heading to prove that the derivative, the limit of the function at a is the same as f of a. So now we have proved this is a given, and this being proved, and now we add a zero, then we take limits. We take limit, okay, on both sides. This is the limit setting. This is not a limit setting. Okay, so we make this by adding zero. So now we're going to take limit on both sides. We take limit on this side, okay? We take limit on the left. Okay, and we take a limit on the right. The whole thing, the whole of the right-hand side. Okay, and we're taking limit as x approaching a. So this is the whole one piece. This whole one piece. Hold on. I need to put a bracket about this. Now, the limit of f of x when x approaching a is equal to the limit of this bracket. Inside the bracket, we see it as two pieces, this piece and that piece. F of a is a constant. F of a is a constant. And this piece has a limit. Constant has a limit. So if we look at limit law, right? So I'm scrolling down the limit law, right? This piece, this individual piece has a limit, and the other individual piece has a limit because it's treated as a constant. So now we can separate the limits. You see, we don't separate the limits without examining the individual limit exists or not. And so this is a typical example, right? So then we take limit separately, like this. Because the individual limit exists. And now, of course, we can just plug in what do we have. The first limit in this expression, this piece, we have it, it's 0. And the next one, f of a is a constant. The limit of a constant is the same as a constant right here, right? So that's f of a. So the limit of f of a is the same as f of a because f of a is treated as a constant. So finally, we got the limit, right? So that is okay. So that equals to f of a. The definition of continuity is satisfied. Therefore, its theorem is proved. Okay, if you look back at this proof, what is being used? We use definition. Okay, what it means for f is differentiable, right? So we apply the definition and the two constructions, right? What we did on this, on the construction of these two, right? The first one is a principle number one. Number one, anything times one stay the same. And the second one, we use principle number two, anything add 0 stay the same. You can see these, we use very basic, algebraic self-evident fact, self-evident truth. But why we use these? Because the limit law. when we apply limit law, before we, take limits separately, in the case of, in the case of product or in the case of sum or difference, we must check the individual limit exists before we can take limits separately. Okay, so this is very, very important. So that's all for this proof. So by this time, with this proof done, we want to re-examine, right? We want to re-examine the relationship between limits, right? Continuity, and differentiability. Limit at the point A, continuity at point A, differentiability at point A, right? When we look at all three, okay, so I'm going to make a table for us to see clearly the relationship between these two. A limit at A, continuity. Okay, so I want to show you, because I want to have a complete narrative for these three very important concepts. Okay, three very important concepts: differentiability. Okay, and of course they're at A, and this is at A, right? At A, and differentiability at A, right? We understand their definitions. We're going to bring these definitions to our, this limit exists means that limit as x approaching A, f of x, it means that it equals to a finite number, okay? And if you look at the fine print, right? X is not, well, X is defined in some open interval. So X is defined at A. Well, X is defined near A, except possibly at A. Near A, okay? Except possibly, okay? Except possibly at A. So what it means is that the function may or may not be defined at A, but we don't mind even if it's not defined at A. But for continuity, where did I? Okay. For continuity, so let's bring up the definition of continuous function at A, right? So this whole thing, this whole limit has to be equal to, so this time we require f is defined at A. So there are three elements, right? So there are three elements. F of A must be defined. F must be defined at A. So f of A is defined. Okay. And of course, that's three elements. The limit exists, right? This limit exists. Okay. And thirdly, of course, that's three elements. Number three, the two are the same. So we actually don't really need this last row. Okay. Differentiability, if we look at the definition, we look at definition of differentiability, right? This particular limit exists. this limit, okay, as x approaching a, f of x minus f of a over x minus a, this exists. That's the definition. But from the theorem we just proved, that differentiability will guarantee continuity. Continuity, one of the conditions in continuity is the limit exists. So continuity also guarantees limit exists at A. Okay, so that's the relationship. So differentiability guarantees continuity, and continuity guarantees limit, but not the other way around. Not the other way around. What does that mean? In other words, limit, if we know limit exists at A, it doesn't mean the continuity will be guaranteed. We need additional information. We have counterexamples, right? So we just need to have a couple of counterexamples, right? Limit and continuity, right? If you reverse this arrow, that's false, right? That's false. Because we have a counterexample. For example, right? Limit, there are plenty of such examples as x approaching 2, right? Or 3, x squared minus 5x plus 6, x minus 2, or, the more familiar example you saw on the midterm exam, and this one has a limit, right? We've seen this, and that limit is, let's just go down the steps, quickly find the limit, right? And the limit is going to be x minus 2 left, direct substitution, 3 minus 2 equals 1. So limit exists. But this function is not defined at 3. It is not defined at 3, certainly it is not a continuous at 3, right? Because one of the 3 conditions, right? One of the 3 requirements. The next one is limit to continuity. Limit to continuity, if we know differentiability leads to continuity, but if we reverse this, right? And that will be false. That will be false again. Continuity does not guarantee differentiability. Do we have a counterexample? Of course. Okay. There are many, many counterexamples. So one of the simplest one is f of x equals to the absolute value of x. And this example is so simple and so useful, so famous, that almost every textbook talks about it, right? This function is certainly continuous, right? This function is continuous at 0, right? But not differentiable at 0. Okay, so how do we demonstrate that? Well, the continuity. So first, we want to demonstrate, right? This function is continuous at 0. Right? To demonstrate it's continuous at 0, all we have to do is just apply the definition. We take a limit, right? We take limit You can consider limit from left or limit from right, but it really is pretty straightforward in this case, right? So that is going to be the limit of absolute value of x. It's just a direct substitution. It's just a direct substitution, and that's going to be 0, right? Which is also the function that's defined as 0, which is the same, right? So continuous is pretty obvious. Second, okay, f is, f is not differentiable as 0. Sorry, I didn't type that. Okay, f is not differentiable. How do we, f is not differentiable as 0. How do we prove that f is not differentiable as 0? Well, we go by definition. We can use either one, right? So we're going to use the one on the top, right? Examine if f is differentiable as 0. All we have to do is to check. We're going to observe this limit. We're going to observe this limit as h approaching 0, right? And the set function is f of 0 plus h minus f of 0 divided by h. So we just have to check if this limit exists. To simplify, because we have 0 plus h, and so we can just simply say f of h, right? And the rest is just plugging in. So we're going to examine this limit. F of 0, we already know that's a 0, right? F of h, that's going to be absolute value of h, right? And to simplify this further, we're getting to this place. So the absolute value of h divided by h. So we're going to evaluate this limit. How do we examine this limit? And we know that the absolute value of a positive number is the same as the positive number. So we have to examine the limit from left and limit from right, right? Limit from left. Let me make the fonts a bit larger. Okay, because the absolute value is in our consideration, and limit from right, right? So over here, when we take the limit, when h is approaching 0 from smaller than 0, the absolute value of a negative number is its opposite. So we get, because h approaching 0 from smaller than 0, h is negative itself, and a negative h divided by h is a negative 1. So this is a negative 1. Oops. What did I do? Oh, I deleted a whole bunch of things. Okay, it's okay, no big deal. Okay, so we examine, I'm gonna just have to retype these things. So this is absolute value of h, sorry about that, minus 0 divided by h. So in the end, we have limits, right? The absolute value of h divided by h. So we observe the limit from left and from right. When we observe the limit from left, which we just did, right? When h is approaching 0, from smaller than 0, the absolute value of a negative number is its opposite. So it's minus h over h. So that ends up to be the limit of negative 1. Okay. And the limit of a constant, of course, is the constant itself. And the limit from right, when h approaching 0 from larger than 0, So when h is positive, the absolute value of positive number is the same as the number. So we're taking limit of a positive one. The limit of a constant 1 is 1. So limit from left and limit from right are not the same. Okay, so this limit from left is not the same as the limit from right. Okay, and what does that mean, right? We're back to that basic theorem, which we have learned a long time ago, that the limit from left and limit from right are not the same. So this limit, right, we will say this limit, we can just drop all of these, does not exist. Does not exist. If this limit does not exist, and by definition of differentiability, the function is not differentiable. Okay, that is the function, right? This function is not differentiable. Is not differentiable as 0. That's it. Okay, so this summarizes what we have learned on limit, continuity, and differentiability. And it also has a closure, as I promised, that each case, if we reverse the arrow, there are counterexamples. And of course, the counterexample we have here is which is one of the counterexamples. There are many, many more. And for that reason, we are now clear about all these relationships. Okay, all these relationships. And I think that's all for this lesson. I hope it's not too long. Thank you for watching. Until next time.